right, and should also share screen. Just trying to get the slides. Wait a minute. Number of slides has gone above 55 now. Right. So that's our topic, at least for the next couple classes. Um, Fluidized beds, very important for industrial applications, as I mentioned. So what I pointed out is that industrially it has been proven, it has been shown to be very advantageous to carry out all these solid catalyzed reactions such as catalytic cracking for all the petroleum applications, for crude oil fractions, etc. So it has been found to carry out these solid catalyzed reactions not in packed beds, but in fluidized beds. Now, fluidized beds somewhat behave like packed beds, but now they have new facets. In other words, the space that you are providing due to the movement of the particles once a certain minimum fluidization velocity is exceeded enables a certain circulation in the bed, which was not there in a purely packed bed. So packed beds led to the occurrence of lot of dead regions where no flow was taking place, and essentially there was no and if there was a reactive system, there was essentially no reaction taking place in those regions. So that was not at all uniform for us. Similarly, if since most of the laws of the solid catalyzed reactions are also exothermic, packed beds are what's the word I am looking for? Well known, no, not well known. I mean, packed beds have a bad reputation of having uh, all kinds of hot spots locally uh, because of these improper mixing and improper due to the presence of slugging, I mean, channeling of the flow and lack of uniform circulation, uniform agitation. And so these hot spots play havoc, especially, for instance, in all of these heterogeneous catalysis, combustion, and all of these applications. So it has been found that we have to expand the bed, right? So this expanded or fluidized bed has all the characteristics of packed bed, but none of the disadvantages that I mentioned. Well, the only difficult part about I can think of the fluidized bed is that all these catalyst particles, they are moving about now, right? They are not fixed as in a packed or a fixed bed. They're moving about. And they collide. Also, they're in constant motion. So, especially at high Reynolds number, there will be an attrition of these catalyst particles. So that's the only disadvantage that I can think of. Um, so you have to all the time substitute or rather regenerate in maybe a different vessel these particles, or continually supply fresh catalyst. But as you know, chemical engineers have perfected all of these things, and these kind of separate regenerator, and then putting in fresh catalyst, um, ensuring that the particles have complete always continually made up. They have actually perfected all of these in the catalytic cracking industry. Okay, all of these Exxon research and all, they were the pioneers of this type of and all patented technologies in catalytic cracking, and they have actually perfected this type of technologies, right? You have um, all the gasoline components from crude oil cracking is produced by fluidized beds. So what, however, today I want to do is discuss some of the more qualitative aspects of this fluidization of this process. In particular, how the pressure drop in the bed, in the fluidized bed, changes with the increase in the Reynolds number. It's a very important characteristics of all fluidized beds and packed beds also. And then I want to indicate how we can use the same force approach which we first did for uh, free settling, then we adapted that to packed beds. We can apply the same approach to fluidized beds, right? And I just want to encourage you to go back to that and write at least the basic balance equation where the pressure drop per unit length of the bed is balanced by the weight of the bed, okay, by the solids weight of the solids in the bed rather, okay. So you know the density of the solids, you know the density of the surrounding fluid, you know the fluid void fraction, just as we did in packed bed, etc. And so you have to write the balance equation. So and then what we can do is once that balance equation has delta P, so the delta P we can use Karman type equation, which I have dealt with in considerable detail. And you can substitute that direct dependence on the superficial velocity, inverse dependence on square of the particle diameter, which is what the Karman equation postulated or rather experimentally showed. So you can substitute that for the delta P per unit length, and now you will have the basic equation for fluidized beds, where the velocity is related to the particle size, porosity, density, etc. Right? And then various design equations can be worked out. I will show you how to do that. But qualitatively, the important thing is, as is in the next slide, is to study the behavior of pressure drop across packed and fluidized bed as gradually the fluid velocity or Reynolds number is increased, and up to a limit the bed remains packed, does not expand, particles stay stationary, so they have all the characteristics of fixed particles, but above an incipient condition, that is above a critical Reynolds number or flow velocity. And as I already described to you, flow velocity we can characterize in two ways, either by looking at the zero epsilon situation, what we call the superficial velocity, or the velocity far away as if the packed bed were devoid of solids. Of course, we can also characterize it by the velocity in the packed bed, and I showed that both of these are just related by a factor of epsilon. Fine. So this particular characteristic of delta P per unit as a function of Reynolds number on a log-log plot shows very distinct 4 or 5 regions. and that is there in the next graph. I've just put it, I hope you can see it. What that figure tells is the relationship. Initially the bed is packed, it's a fixed bed. It shows you on the y-axis the logarithm of the pressure drop across the bed. On the x-axis it shows you the log of the Reynolds number. So at a very low Reynolds number, which in this figure is characterized by point A, the bed is very nice and stable. It's a perfect fixed bed and with low pressure drop. But that is because your flow velocities are small. But as I told you, gradually many times most of the beds can't operate at very low flow rates.
Sir, is this an experimental data? The
Yes,
plot
yes,
of
yes. This is experimental data over large number of beds, which summarizes the information as you go from a packed bed and fluidize the bed. This is the 5 stages of, is well known called 5 stages of fluidization. Coulson and Richardson doesn't talk about these stages, but other books such as uh, McCabe's book, I don't know if it doesn't have this diagram. It talks about these various stages. Okay, anyway, I'll describe them to you. Yeah, so this is a generic pressure drop behavior as you convert a packed bed to a fluidized one. So initially, you are at a lower left hand quadrant of this, lower left hand corner of this graph. At point A, the bed is very stable and nice in that sense. And the pressure drop and the Reynolds number are all related by the equation that we gave were given first by Karman, and which I gave you earlier, which is K double prime times 1 minus epsilon whole squared upon epsilon cube multiplied by mu times the superficial velocity divided by square of the assuming it's spherical particles, square of the particle diameter. That was really what the equation told us. So that is what you have at point A. Now, gradually you are increasing between point A and B, you start increasing the flow velocity or superficial velocity, or also which also the velocity in the bed. So as you increase the delta P, starts on a log scale, it starts going up linearly. Okay, and then you come to point B where the pressure drop, essentially it is balancing or rather the bed solid's weight is balancing the pressure drop, right? And that's the equation I want you to write, and then we can look at this tomorrow quantitatively, right? This region. So at B, the pressure drop is balancing the weight of the solids in the bed. Now suppose you further increase the Reynolds number. Now the bed is no longer stable. As you grow from B to C to D, etc., the bed has what it's no more a fixed bed, and we call the bed fluidized. So basically between the points B and C, this bed is sort of unstable, and now the particles have started to move about. The particles are adjusting their positions. They adjust their positions in such a way that they minimize the resistance to the flow. Okay, and for this the particles have to spread out and the entire configuration has to become much looser, a loose configuration with much higher voidage epsilon than you can ever do in a packed bed. For instance, various packing patterns you have already done in material science, and I would expect none of those HCPs and FCCs and etc. face centered cubic and all, none of those are valid for the fluidized bed. The packing is much looser, and the loosest arrangement is obtained in this figure at point C. Even now, the particles are sort of, they have begun to they are initially they, you can say that this is the point of incipient fluidization between B and C. In other words, earlier the beds, you can say the particles were almost in contact, and there was some void fraction, voidage epsilon between those contacting particles. Now gradually they will start to move apart. So that is somewhere between B and C. McCabe-Smith says C is the point of incipient fluidization, which is the maximum that you get in this curve. Okay, let us have it like that. I think it's somewhere in between B and C. Doesn't matter. We are not nitpicking on that. But what happens now is you still start to increase flow velocity. These particles which were in contact, now beyond that point B or C in the notation of McCabe, the particles are now moving and they are colliding also. You can say that there is somewhat a more hindered type of settling is take place beyond point C. As you further increase RE and say you reach a point D, the particles are now all in motion. And once the particles are in motion, as at point D, if you further increase RE, then it is found that the pressure drop increases very, very slowly beyond D. And there is a slight increase, small increases in delta P as the bed continues to expand and the particles movement becomes more rapid, is there between D and E, but very, very small. And beyond E, of course, if you keep increasing the flow rate or the superficial velocity, of course, the particles will start streaming with the enhanced flow that you are supplying, and they will elutrate out. There will be elutriation, and the bed itself will stop existing. That is the point E that is drawn in this figure. So basically, there are these 5 points that is distinguished between packed and fluidized bed. First, the bed is packed, fixed, particles are in contact, pressure drop is very low, flow velocity very low. Gradually, as you increase flow velocity or Reynolds number, the pressure drop increases, but the bed still remains packed and the fluid particles are in contact. But when you go beyond a critical value of the flow, the particles are no more in contact but begin to move freely. And that point is the point of incipient or fluidization, which is the maximum of this curve, point C. And then point D is reached, the particles are totally in motion. and further increases will change delta P only very small, and there is no drop at least in delta P, or no major increase. And beyond DE there is no bed at all. So this is the categorization of the transition from packed condition to a fluidized condition of the bed. There are many more interesting experimental observations. To answer Himanshu's question, there are a large number of experimental information in this. I have only tried to summarize them. Uh, it is found that in general, when the bed is fluidized, there are two major uh, you can say regimes of fluidization. One is called particulate or particle fluidization. The other is called aggregate or aggregative fluidization. So what do we mean by these terminologies? Now, once we are beyond the packed bed region, we are into fluidization. However, we are nowhere near E or between D and E. In other words, relatively in the fluidized condition, the superficial velocity is lower. You can say that when will that happen? When the particle size is small, or the density between difference between solid and fluid is small, or both, and so the flow velocity is relatively low. Even in the fluidized condition, you are very near C. So the bed is fluidizes very evenly.
Sir,
Yes,
sir, this graph log of the minus delta P versus log of NRE. Sir, we can say that when we are going from A to E, then our regime is changing from the changing to the fluidized bed
correct.
from
From
the
packed
packed bed.
condition.
So
Yes, yes,
from packed bed to fluidized bed, these are
correct.
the things.
These are
And
the
sir,
things.
sir, one more thing. Sir, what how the particles behave in the fluidized bed versus in the packed bed, sir? Can you just give me some insights? Like, is there any difference in
Well,
the
I have made a
velocity?
large number of movies on this. The thing is, it's a question of are the particles in contact or not in contact. In a packed bed, depends by the type of packing. We only considered uniformly packed things, but you can actually pack them, as you know from material science, in several types of packings. But the voidage can be changed. But particles are in contact. However, once you pass point B or C, and the particles are now, they have their own independent motions. They are separated. However, between C and D or so, it's an even kind of motion, even though the particles are moving individually. Still, the bed as a whole behaves in a uniform way. That's what the chemical engineers have found by a lot of films and movies and tracer techniques. So it's like this, there is some mean path, mean free path that the particle goes through. It's more like a liquid. It still behaves, the dense phase is also like liquid, but they call this uniform kind of fluidization particulate fluidization. However, as you go beyond the D, and the flow velocity is very high, or let us say the densities are very different, or the particle size is very large, dp is large, then the bed is not uniform anymore. There are lot of multi-phase type of bubbles for a nucleation of bubbles, and they start putting the particles, they're spraying the particles all over the place. Once these bubbles come and burst, and there are a lot of research on this, they spray the solid particles above the bed. So the bed is more like a liquid with gas that is bubbling through it. And this condition between, say, D and E is called aggregative fluidization. So in other words, there's a lot of instabilities of due to the large bubbles of air or liquid or air or gas or whatever. And all of these, how these behaviors are changed by based on how the distributor that spreads this gas, and all this chemical engineers have freaked out, and there is a hell of a lot of information on
Sir,
this distribution. Okay. So what I have tried to do today is to describe the qualitative features of the fluidized bed and how this is changed as you increase the gradually the flow velocity or the Reynolds number. Now what I want to encourage you all to do is to apply the same force balance that we did for packed bed to the fluidized bed, and then adapt Cosen's equation, substitute it for delta P by L, and tell me what you get. And then I shall tomorrow indicate how we can improve that, or how others have improved that, those correlations, and what sort of design equations are used for predicting pressure drop in fluidized bed. And finally, about maybe by 31st March, I shall give you these very nice correlations, which are again over several decades of Reynolds. Okay, thank you very much. And we will continue on this way. And then April, we will move on to filtration applications and maybe centrifugation. Let's see how far we go. And then you have to, meanwhile, get your presentations ready. Okay, good luck. See you tomorrow.